Okay, so we're going to start in on our next chapter. We got a new functional group here. So this will be chapter 9 on alkynes. All right, and so just as a reminder, we started out by talking about alkanes, carbon, hydrogens, all single bonds. We then graduated to alkenes, our carbon-carbon double bonds, molecules that contain at least one carbon-carbon double bond. And now we're going to graduate to alkynes, which have carbon-carbon triple bonds. All right, so first thing that we got to get good at is drawing our alkynes. Alkynes, because of those sp hybridized carbons, they have a linear geometry. And so when we draw our alkynes, we're going to be really good to draw that linear geometry, right? Not only are sp hybridized carbons, but also what they are bonded to. We have all 4 of these atoms all in a straight line here. All right, what we don't want to do is draw our alkynes like we would our alkenes or our alkanes in our little zigzag. This right here would be incorrect. Okay, again, we got this linear geometry. Remember, these are sp hybridized carbons, which means that they have a linear geometry. So when we draw our alkynes, we're going to make sure to draw that linear geometry. Importantly, your homework system will totally accept this like kinked up structure like this. This would get you points off on an exam. All right, you're going to make sure to be good and draw your alkynes with that linear geometry. All right, so first place, we're going to start talking about our alkynes, our physical properties. All right, so in terms of polarity, what do we think? Polar, nonpolar? Nonpolar, we're still just only carbons and hydrogens. We don't have any polar bonds at all. So these are still our very nonpolar compounds. Which means in terms of boiling point, what do we think? High boiling points or low boiling points? Again, yeah, weak interactions with one another. So we have our very low boiling points. All right, so we're going to make a note here that in terms of very low boiling points, we mean compared to the other functional groups. All right, when we start talking about polar functional groups, we'll have higher boiling points here. All right, but we're going to compare now to our other 2 compounds, our other 2 functional groups that we've learned about here. And remember, both of these were also very nonpolar and had very low boiling points. So if we compare the 3 here, how do these look? All right, so importantly, I'm going to tell you that alkynes, all right, our alkynes have more surface area than alkenes or alkanes. It turns out that because of that linear geometry, these molecules are able to pack together much more efficiently. All right. So if we have more surface area, what does that mean about our boiling point of alkynes versus alkanes or alkenes? It would be higher, all right? So out of these 3 carbohydrons here, hydrocarbons rather, more surface area our alkynes have higher boiling points than the other two. All right, and just now tying this into what we learned before, all right, we said that alkenes actually had less boiling point, smaller boiling points than alkanes. So that means our alkynes have higher boiling points than alkanes, and our alkenes have the lowest boiling point. All right, so alkynes greater than alkanes, greater than alkenes in terms of those boiling points. Okay, so now let's say that we're comparing two alkynes. All right, what about longer chain length? What will that do to our boiling point? Increase or decreasing? If we have a big alkyne, is that going to have a higher or lower boiling point than a little alkyne? It's going to be higher. All right, same trend that we saw with alkanes and alkenes. All right, what if we have more branch points in two alkynes that we're comparing? Is that going to have a higher or lower boiling point? More branch points would decrease our surface area, so that would be lower boiling points. All right, this is the same trends as alkanes and alkenes. All right, universally true here. There's one more thing that we talked about with regard to alkanes and alkenes, and that was what happened when we make a ring. I'm going to leave that off of here, though. Why do we not worry about rings with alkynes? We can't have them. Why can't we have them? Because of that linear geometry. You would have to have a ton of carbons. I mean, I bet if you had 20 carbons, you could have a ring, right? But practically speaking, you're not going to see alkynes in rings because they have to have this linear geometry, which is not really conducive to a ring geometry. All right, so we're not going to talk about ringed alkynes. Okay, our next physical property is their appearance and odor. Okay, and we're just going to note that these are the same as alkanes and alkenes. Can't really distinguish the three functional groups, our three hydrocarbons, based on just their appearance or odor. All right, and lastly, we've already talked about this, but just to note our geometry. Okay, if I'm going to draw, let's say, a very large alkyne, I can start drawing my zigzaggy structure. But once I get to that carbon-carbon triple bond, I have to draw that linear, those four atoms in that linear geometry. Okay, so again, these are sp hybridized carbons, meaning they're linear. So I'm going to draw not only that carbon-carbon triple bond in a straight line, but also the other two bonds. All four of these atoms lie in a straight line. All right, we talked about how the geometry led us to conclude that those alkenes were more reactive, right? That pair of electrons was really easily accessible because of that trigonal planar geometry. Same thing with our alkynes. This is a very flat region of our molecule, so things have an easy time accessing those electrons there. Another key about those electrons that made them so reactive is our alkynes. We have a carbon-carbon bond. One of them is a sigma bond. And what are the other two? Pi bonds. So now we have not one, but two pi bonds in our alkynes. All right, and so we'll talk about our reactions of alkynes here in a bit, but we're going to see that there's a lot of overlap between alkyne reactions and alkene reactions. They both like to undergo those same addition reactions because, again, we have our pi bonds that are leading to the reactivity of these functional groups. All right, and now we're going to very quickly go through the nomenclature of alkynes. All right, and that's because there's only one thing that we have to update here, which is our parent chain suffix for our alkynes. We're going to use the suffix YNE. All right, and now for everybody's favorite part, stereochemistry. We had our RS stereochemistry for our alkanes, for our tetrahedral carbons. We had our EZ stereochemistry for alkenes. Alkynes don't have stereochemistry. There's only one way that you can orient these two groups around that triple bond, and that is in a straight line. All right, so fortunately for us, we're just going to note we got no stereochemistry to worry about for our alkynes. All right, so keeping this in mind here, let's go ahead and name the following alkynes. Oh, let's put a methyl group on here. All right, so I'm going to find my parent chain. 2, 3, 4. This is the biggest mistake that people make with regard to alkynes, is forgetting that there's got to be a carbon on either side of that triple bond. Right? So this molecule here has a total of 4, 5, 6, 7, 8 carbons associated with it. We're going to number our parent chain. We're going to prioritize that functional group. So I'm going to number this way here. We see our triple bond is located between carbons 2 and 3. So just like alkenes, we're going to refer to it by the lower of the two numbers. So this would be 2-octyne. Got that YNE suffix for our alkyne. Or if we wanted, we could move that 2 to the back, so oct-2-ine. Either one of these would be acceptable. All right, over here, 1, 2, 3, 4, 5 carbons, which means that this one up here is a methyl group. All right, when I number my parent chain, I can go in two directions. Which one of these is going to be correct, red or blue? Red, because I'm going to prioritize my functional group here, prioritize that carbon-carbon triple bond. I'm going to include my methyl here, so this would be on carbon 4. So 4-methyl 1-pentyne. All right. Did we talk about moving this into the back half of the name? Does this look familiar to anybody? Okay, you know what? Don't worry about it. We'll cross that bridge when we come to it. Either of them are acceptable. I mean, I guess I've already started it, so let me just go this far. Don't worry about it. There's going to be a time when we have to put it in the back half of the name, but we're not there yet. But just to kind of complete this, we could move that functional group location to in front of that functional group suffix, and either one of these are considered to be perfectly acceptable in the IUPAC naming scheme. If that doesn't look familiar, don't worry about it. Stick with what we know.
Will we get docked if we don't include the location for the triple bond?
Absolutely.
Okay.
Yep. You have to include the location because there's 4-methyl-2-pentyne. That's a different molecule. So yes, you do not get to assume that your functional group is in any position. I guess the one exception would be, or an exception would be something like this. What would this molecule be? Not meth. How many carbons? So this is ethyne. Why don't I have to say it's 1-ethyne? There's no other way, nowhere else for me to put it, right? So just by saying ethyne, I have uniquely identified the molecule. Cool. All right, so let's move on and talk about reactions of alkynes. Sort of a good news, bad news thing. Yes, we have more reactions that we're learning here, but the good news is we're going to see a lot of familiar reagents, a lot of the exact same reagents that we saw with our alkenes, and that's because alkynes also undergo addition reactions. We got those same pi bonds. We're adding to either side of those pi bonds. So we're going to see a lot of the same reagents, HBr, Br2, all that stuff that we saw last chapter. We're going to be repeating here with our reactions of alkynes. All right. We're going to start with looking at a hydrogenation reaction. All right, and so let's take our simplest alkyne, our ethyne. We'll draw out its full Lewis structure so it's super clear what's going on here. All right, and everybody's going to do an addition reaction, a hydrogenation reaction, the addition of H2. All right, predict what our addition products would be here. All right, we add a hydrogen to either side. Okay, so we break our pi bond. So if we hydrogenate an alkene, or dang it, gave it away a little bit, hydrogenate an alkyne, we get what functional group? An alkene. All right, but what do we know about alkenes? Can't I hydrogenate alkenes as well? Yes, and so that we could hydrogenate to an alkane. And this is going to be a big difference with what we see in our alkynes versus our alkenes, is often we can do one or two steps because we have those two pi bonds to work with here. All right, so we can hydrogenate an alkyne to an alkene, or we could further hydrogenate that all the way to an alkane. Now, we talked about how these hydrogenation reactions, although they're very thermodynamically favorable, which means it's really easy to break these bonds, and then the bonds that you make, you get a lot of energy released, right? So thermodynamically favorable reactions, but very kinetically slow. So we always had to use a catalyst here in order to actually do our hydrogenation reactions. And we're going to see the same thing, but it depends on whether you want an alkene product or an alkane product. All right, so let's first revisit the one that we learned last time, our hydrogen gas and that palladium or platinum catalyst. All right, if we take an alkyne and we treat it with our hydrogen in the presence of palladium or platinum, this method here is a very strong hydrogenation method. You will hydrogenate to an alkene, but you won't be able to stop there. It'll blow right past and give you your alkane product. You'll always get your fully reduced, fully hydrogenated product here, an alkane. All right. To be clear, what we've done is we've added hydrogens to either side of that carbon-carbon triple bond, but we've done it twice. When we did this reaction before, we had to worry about the fact that this was this syn addition, because that would determine the stereochemistry of our product here. Do I have to worry about my stereochemistry of this product? No. Fortunately, I'm adding the same thing to the same carbon twice, so there is no way for these to be stereocenters. These reactions are not stereospecific. All right, we'll kind of summarize these on a little cheat sheet next time, but we can note no stereochemistry to worry about. What about regiospecificity? Same bond on either side, so again, no regiospecificity as well. We're always just going to be converting our alkyne to an alkane in the presence of that same palladium or platinum catalyst. All right, but what if I really want to stop here? What if I really want to stop at my alkene product? I don't want to reduce all the way to an alkane. Well, you're in luck. We got ways to do it. All right. The first is what's called, they call them poison catalysts, meaning they're catalysts that aren't as great. And the first one is what's called Lindlar's catalyst. And Lindlar's catalyst is when they take palladium and make it just not as good of a catalyst. When we'll see it in our chemical equations, it'll just simply be listed as H2 and Lindlar's catalyst. All right, as I said, this is still that same sort of solid state palladium catalyst. So those solid state catalysts, they imply we're going to get a syn addition. All right, syn addition meaning what? Those hydrogens are added to the same side or opposite sides? To the same side. But now I'm going to have an alkene product. So if I add my hydrogens to the same side, my methyl groups will then be pointed on the same side as well. All right, so we can note that this will always give us what? The E or the Z stereochemistry for our product. So it'll be the Z stereochemistry for our product. So this will reduce that alkyne to an alkene, but it will be a stereospecific reaction, giving us a particular stereochemistry, notably the Z stereochemistry of that alkene. All right, so then what if I want an alkene, but I don't want the Z stereochemistry, I want the E stereochemistry? We got another set of catalysts that we can use. Specifically, we're going to use either sodium or lithium, one of those group 1 metals, in liquid ammonia here. All right, as noted, let's use this same alkyne. Of sodium or lithium in ammonia. That'll give us our alkene product, our addition of hydrogen, but now we will specifically get the E stereochemistry. All right, so what's going on here? I'm going to do the reaction mechanism. This is not one of these reaction mechanisms that I expect you to know off the top of your head, like some of the other ones that we've been talking about. This is just for fun here. All right, I think it's interesting. It also will illustrate something that we're going to see a little bit later on as well. So just to kind of introduce ourselves to that. All right, what's interesting about this reaction here is we're not using sodium ions or lithium ions. We're using actual sodium metal, right? Neutral sodium, which means that it has 1 electron. Okay, and remember, electrons, they don't really like to be unpaired here. So what happens is this sodium is going to donate its electron to one of these carbons. All right, well, that electron doesn't want to be unpaired, so what's going to happen is this bond here is going to homolytically cleave, and it's going to evenly split apart. 1 electron going one way, 1 electron going the other way. All right, and what you'll notice that's different about these electron pushing arrows here is these are these fishhook arrows here. Not a double-headed arrow, but a single-headed arrow here. All right, these fishhook arrows. And we use them to show the movement of 1 electron. All right, mostly every time that we've seen these arrows up until now, it's been showing the motion of a pair of electrons. This is now showing the motion of just a single electron. One from the sodium to this carbon atom, and then within this pi bond here, 1 electron goes one direction, the other electron goes the other direction. All right, so this creates our carbon-carbon double bond here. We've broken our carbon-carbon triple bond. Importantly now, we got this pair of electrons. All right, let me color code here. One of these carbons has 2 electrons associated with it. All right, that anion it's got a negative charge here. This is a carbanion. The other one just has 1 electron, 1 unpaired electron here. And this is what we call a free radical. And we'll talk about a few reactions that involve free radicals. All right, but suffice it to say, they're pretty mad. Electrons don't like to be unpaired. Okay, so in the next step, now our solvent is going to be important. That carbanion is going to reach out, grab that hydrogen. Notice now I'm using a double-headed arrow because I'm showing the movement of not 1 but 2 electrons. All right, so we got a hydrogen over here. We still have our very angry unpaired electron. Another sodium atom's going to come and again donate that now to this radical. So now we have a paired electron, an anion. All right, and just as we saw previously with that anion, it's going to be protonated by our solvent, giving us our alkene product. Specifically in that E stereochemistry. All right, and why do we specifically get that E stereochemistry? Because in this first step here, these 2 groups of electrons, they want to be on opposite sides, right? There's a lot of negative charge concentrated in these 2 orbitals. They don't want to be next to one another. So our E stereochem, because these orbitals here want to be on opposite sides. Cool. So again, this mechanism here is not one I expect you to know. It's just kind of for fun here. I think it's interesting that this sodium metal is involved. You really don't see sodium outside of its ion state very often. So the idea that we're working with sodium metal is pretty interesting on its own. And it's that unpaired electron there that leads to this weird kind of reaction that we need to illustrate using these new types of electron pushing arrows, these fishhook arrows. And we're going to talk about more radical mechanisms as we move forward in the course, which will use these fishhook arrows. So I just kind of want to throw them out here now. we can get a look at them. Cool. All right. So we got hydrogenation reactions, adding our H2 to our alkynes. We can either fully hydrogenate to an alkane using our method that we learned in the previous chapter. All right, because like we said, yes, this will hydrogenate an alkyne, but we also know it will hydrogenate an alkene. So that gives us our alkane product. If we really want to stop at that alkene step there, we're going to have to use one of these new fancy ones here, either Lindlar's catalyst, which will give you that syn addition, or this new fancy method using sodium or lithium metal in ammonia, which will give you that anti-addition. So Lindlar will lead to the Z product, whereas our sodium and ammonia or lithium and ammonia will lead to the E product. All right, so another familiar one that we've seen before. Are halogenation reactions. All right, so just to use, let's start out with our very simplest alkyne, our ethyne. Now we're going to add our halogen. Okay, and just like we saw before, when we add this halogen, we're going to add it in an anti-addition fashion. So everybody take a second and see if you can't give me my alkene product here with those halogens added as that anti-addition. All right, so we're going to replace our carbon-carbon pi bond with these two single bonds, but I'm going to make sure that my halogens here are on opposite sides, which leads to what stereochemistry? E or Z? So these halogens are going to be your higher priority groups, even if this was carbons, right? Halogens have a higher atomic number. So this is specifically the E stereochemistry that we're going to get. But we know alkenes can also be halogenated. We also know that these are anti-additions. But is my product here going to be stereospecific? Right? We talked about how these reactions were those anti-additions, right? But if we look over here, is this a chiral carbon? No, why not? Because it's got two halogens on it. What about this one? Is this a chiral carbon? No. So again, we don't have to worry about our stereospecificity of our product since we're adding the same thing twice to that same carbon. All right, so our product here is not stereospecific. All right, unlike our previous hydrogenation reaction, this reaction did not have to be catalyzed. So we can simply tune whether we're going to get one addition or two additions based on how much of that halogen we add. So let's grab our example alkyne. I'm going to put it in the middle here. And over in this direction, we're going to add just one equivalent of our Br2. Whereas over here, we're going to add two equivalents of Br2. Right? So to be clear, by one EQ, I mean one equivalent. Meaning however much alkyne I have, I'm going to add that same amount of bromine. Whereas if I had two equivalents, that means that however much alkyne I had, I would add twice as much bromine. So one equivalent would give us one addition. Two equivalents would give us two additions. All right, so given what we discussed above, everybody take a second, see if you can't predict the products here for these two reactions. All right, so two equivalents. I'm going to get two bromines on each carbon. Okay, again, we don't have to worry about stereochemistry at all because these are, although they're tetrahedral, they are not stereocenters. They don't have four distinct bonds. If we do one equivalent, we're going to get an alkene product. Are my bromines going to go on the same side or opposite sides? Should go on opposite sides, right? That anti-addition. So one bromine up here, one bromine down here. It's going to drive me nuts. All right, so just like we saw before with our hydrogenation reaction, with our halogenation reactions, we can have one addition of our halogen or two additions of our halogens. Unlike before, it's not catalyst dependent. It's just how much bromine I add in there. Do I only add one equivalent, so I only get one addition, or do I add twice as much bromine as I have alkyne, giving me those two additions? And we just note, if we do add one equivalent, we need to make note that it's that anti-addition, so we get that specific stereochemistry. To be clear, it's also anti-addition in the second step. You just don't really care because you don't produce any stereocenters. All right. And then we can also do our hydrohalogenation reactions. All right, in our hydrohalogenation reactions, we're taking our alkyne and we're adding that hydrohalogen or that hydrohalic acid, HCl, HBr, or HI. All right, take a second and predict that first addition product for me. All right, we added our H to one side and our halogen to the other side here. Do I have any specific stereochemistry of my product? No, right? This is neither E or Z. These two are identical here. All right, if we do it again, though, there is something that we have to consider, something special to consider. All right. And what we're going to see with alkynes, and we'll talk about this a little bit more in the next class period, but the mechanism of these alkyne reactions are not as well understood as they are for our alkenes. So we don't really have a mechanism for this first step like we did in our alkene reactions. But we do know this second step here, our alkene playing the role of the nucleophile will attack that electrophilic acidic hydrogen. And we'll again get this carbocation intermediate. All right, so importantly, one side gets the halogen, the hydrogen rather. The other side gets the carbocation. And it turns out that those carbocations will form more stably on the carbon that contains the halogen already. All right. Our carbocation here is more stable on the carbon with that halogen. So it doesn't form on the other side of my carbon-carbon double bond. It forms on the same side. All right, so then given our halide ion, our nucleophile, go ahead and finish off this mechanism. Okay, so importantly, both of our halogens, if we do this reaction twice, are always going to be added to the same carbon. Okay, because in that second step we form a carbocation intermediate, and that carbocation is more stable on the carbon that already contains one halogen. that's where my second halogen will be added as well. Okay, so we used a very simple alkyne to start out with. Let's use a slightly more difficult alkyne and keep that up there. All right, and we're going to use this one to talk about the regioselectivity of these reactions. Oh my God, I hate you. Okay, so again, we're going to be able to control how many additions we have based on just how many equivalents of our reagent we use. So let's go ahead and add 2 equivalents of HBr. And we know that that bromine is going to be what? Added to the same side or opposite sides? And we add it to the same side, right? When we have 2 equivalents added, those 2 bromines are going to go on the same side. But now, it's going to depend on which one I choose. Notice that this red carbon here is a primary carbon, whereas my blue carbon here is a secondary carbon. All right? Well, just like our addition of HBr to our alkenes, this is a Markovnikov reaction. So I know I'm going to add that bromine to the same side, but specifically which side is that going to be? Primary or secondary? Secondary. That more substituted carbon is going to get those 2 bromines. I didn't draw it, but we're going to fill in with our mind's eye here. How many hydrogens were there on that primary carbon to begin with? 1, and how many are over here in my product? Right, so we did also add those 2 hydrogens. We just don't have to explicitly include it. All right. Do I have to worry about my stereochemistry of my 2 equivalents being added? Do I have any stereocenters in my alkyl halide that's produced? No. Okay. Because I added the same bond twice. Yep. All right. We do have some stereochemistry to consider if instead we were to add just 1 equivalent. So let's now do our stereospecificity. Stereoselectivity, whatever, same thing. Now we're just going to add 1 equivalent. All right, in this case here, is one of these carbons going to be more preferable than the other? No, they are both secondary carbons. And notice those are my only 2 options, right? Because of that carbon-carbon triple bond, it can either have 1 carbon neighbor or 2 carbon neighbors, but it can't have 3, right? Because it's already got a triple bond to its neighboring carbon. So in this case, since this is also symmetric, I don't have to worry about which one I pick. But nonetheless, I would get two possible alkene products here. Because just like we learned for our hydrohalogenation of alkenes, it isn't an anti-addition or a cis addition. You get a mixture of both. So this would be my anti-addition product. But not cis, I'm sorry, syn addition. Or I could do my syn addition product. And these are indeed two distinct molecules. All right, I'm not allowed to rotate about that carbon-carbon bond, carbon-carbon double bond specifically. So these two here, either I have these methyl groups on opposite sides, or I have these methyl groups on the same side. All right, so these are two distinct possible products here. They're not produced equally though. Okay. Unlike before, I got a mixture of syn addition, anti-addition. I had a perfect racemic mixture. Here we don't have a perfect racemic mixture. It turns out that this is my major product, and this is my minor product. And it has everything to do, so why is that the case? It has everything to do with the location of those two big alkyl groups in my molecule. On my major product, those alkyl groups are on opposite sides. And in my minor product, those two alkyl groups are on the same side. All right. So why is the major product where those alkyl groups are on opposite side? Well, do big groups want to be located right next to each other, or would they rather be as far away as possible? They want to be as far away as possible. And that's even more true the bigger this group is, right? It's just a methyl group in this case. If it was an ethyl group or an isopropyl group or something like that, the distribution of major and minor would even more favor the major side here. So this is our major product, because our big groups, those big alkyl groups, want to be as far apart as they can. All right, cool. So then the last one that we're going to cover, another familiar one, are these ozonolysis reactions. All right, remember, these are a little bit different. These aren't addition reactions. They are oxidative cleavage reactions. All right, and so just to remind ourselves, when we had an alkene and we did our oxidative cleavage, we took this alkene and we broke it into these two chunks. Right? We cleaved at that carbon-carbon double bond. And it's an oxidative cleavage because when we broke this thing in half, what did we put on the other end? An oxygen. right, so that was our oxidative cleavage for our alkenes. For our alkynes, okay, let's get another example here, but instead of that carbon-carbon double bond, we're going to put in that carbon-carbon triple bond. All right, of course, I'm going to be good and draw it in that linear geometry. All right, our reagent list is going to look really similar, except instead of DMS, I'm going to use water in my second step. The key here, the thing I'm focusing on is that O3 to let me know that this is, again, that oxidative cleavage reaction. Because, again, I'm going to take this molecule and I'm going to chop it at that carbon-carbon triple bond. Okay, but if we try to play the same game, it's not going to work out too well. Meaning if I try to just stick an oxygen here, that's not going to work. Right? I can't have a carbon-oxygen triple bond here, but I still want that fully oxidized carbon. So instead of having a carbon-oxygen triple bond, I'm going to have one carbon-oxygen double bond and one carbon-oxygen single bond, creating what functional group? Carboxylic acid. All right, so that's our big difference here between these two. We still have that oxidative cleavage. We still cut it in half. We're still going to oxidate that carbon as much as we can. All right, but now our two fragments, instead of being carbonyls, will be carboxylic acids. All right, so again, we still chopped it at that carbon-carbon triple bond. We still added an oxygen to the other end. In this case, it was just the one oxygen because we could make a carbonyl. In this case, to fully oxidize that carbon, we had to have two, a carboxylic acid and a carbonyl group, or rather, a hydroxyl and a carbonyl group, giving us our carboxylic acid. Cool. All right. We'll pick up with this next time as well, finish off our discussion of alkynes. We also have hydration reactions of alkynes. We'll cover that next class period.